All right, there are 3 Zemax files to download on Blackboard. You might want to do that while I get everything set up. I'm going to wait another minute or two since I don't have everyone here. Okay, so here's ideal imaging. And as we discussed last time, here's what actually happens. We get rays that do not go where they're supposed to go. Ideally, the rays would go all to there, but instead they spread out. And we spent some time trying to understand that. And if we call this Y1, and we call this Y2, and we call this distance R, then we found that Y2 is equal to magnification times Y1 plus spherical aberration times R cubed plus some coma coefficient times R squared times Y times some function of theta, the angle in the plane. And then there are additional terms. There's an astigmatism term. It's multiplied by R, and oh, that should be Y1 squared times another function of theta, and so forth. And we said that each of these terms corresponds to a different qualitative effect. And what you should have found when you did the Zemax assignment for today is something a bit like what I'm about to share. You should have gotten something like this. If we were to plot the spot size or plot the log of the spot size versus the aperture diameter, I know that this isn't really readable, so let me edit the font. Is it going to let me do that? Okay. Let me try to get the whole thing. You should have gotten that spot size is proportional to the cube of the aperture diameter, for the simple reason that where the rays are arriving in the image plane, how far off they are from where they're supposed to be is proportional to the cube of R, the cube of how far from the center of the lens they are. Any questions on that? Anyone? Anyone? Everybody got exactly that.
Oh, wait, no, I retract my thumbs up.
What?
Sorry, I put a thumbs up, but I retract it.
Oh, you didn't get that?
I can't actually see. Hold on. What is that? Y equals 2.9?
Well, you know, if you have a different set of configurations, you might get a different constant. Remember, I said in the instructions that I don't care too much about the details of the lenses. So the coefficient out front might be different, but it's going to be x to the 2, it should be x cubed. When I did the fit, I got x to the 2.9882, which is very, very close to x to the 3.
Oh, yeah. What you wanted was a slope. Yes, yeah. Okay, I got 3. Yes.
Yeah. Okay. Now, what you should have also found is if we go back to the formula, this is, well, we're only going to have to worry about this term if the object is on axis. Right? If that object is on axis, then y1 is 0. And so we're not going to have to worry about the second term or the third term or so and so forth. But if it was off axis, then we're going to have a term that's proportional to r squared y1 and r y1 squared. All right. And so if we go back to the spreadsheet, then we should get, if we look at off axis, depending on what situation we're in, we're going to get something that's kind of messy. If we have large, it could be proportional to r squared or r. It's no longer a simple dependence because now we've got this r cubed term and r squared term and an r term, and the interplay of them means that in principle, you're just going to get a mess. It's going to be hard to distinguish them with the things that we've done. But you should have gotten a much messier dependence as we move it off axis. Any questions so far? Well, let's go into Zemax. Now, I don't know about you guys, but I found that this was the best configuration. And the reason goes back to this highly optimized lens where there's a small deflection at each surface. All right. If we go into this, if I were to flip these around, which I would do just by going into the lens data and '20 and infinity, then it's hitting, the rays are hitting the surface at a larger angle because the surface here, because it's curved, it's bending away from the rays. All right. And if it's bending away from the rays, you're going to have an even larger incident angle. And large angles mean that we can no longer make the small angle approximations that underlie all of this theory. And so that's why this configuration turns out to be worse. Any questions on that idea? Well, one perfectly fair question would be, what if we flip this around? I make this one 61.865. and I make this one 15. And I go back to my layout, and you could say, all right, well, we've got the, oh, wait a minute. You could say, okay, well, shouldn't this be optimal for this situation then? Because if I turned, right now, I've got the rays coming in and hitting a flat surface. If I flip the lenses around, then I'm going to have them hitting a curved surface. And the thing to understand is that if the lens is asymmetric, there's no getting around the fact that at some point the ray is going to have to pass through a curved surface. And when we're doing real imaging like this, it's going to have to approach the curved surface. If I just flip it around going like this, it's going to have to approach the curved surface while the surface is curving away from it. So sometimes rays are approaching a surface that's curving away from them. Well, if the surface is going to curve away from the ray, I would rather have that the ray be making a smaller angle with the axis on that side than a larger angle. And in this situation, the larger angle is here. Well, that's got to be bad. Let's verify that that's bad. I'm going to start by just making sure everything is in focus. And we're going to check our spot diagram. Why is it? Okay, there. And we get 11.3. And then I'm going to flip the lenses. And do another quick focus. And check our spot diagram. And it's substantially smaller. And so the thing to think about is that when the surface is curving away from the ray, you want the ray to be making as small of an angle from the axis as possible. And that means that if we're doing a situation where the image is demagnified, in other words, image distance is shorter than object distance, then we want to have the curved surface where S is larger. So that's making the smaller angle here. Any questions?
I have the same setup as you.
Brady, Spencer, I can't quite hear you.
Hear me better?
Yeah, I'm turning up my volume. Say it again. You have what?
So I have the same setup as you. We're
Yeah.
actually looking at mine now. I have it flipped the other way. I kept receiving virtual images whenever I quick focused it.
You keep seeing virtual images?
Yeah.
Oh, well, that's probably because your lenses are too close to the, sorry, your object is too close to the lenses.
Okay. So yeah, I achieved the same results and got the same values. I was just double checking and making sure that's not going to affect.
So what you got then is you got virtual images and you found the spherical aberration in the virtual images. Is that what you're saying?
Yes.
Okay. Great. Virtual images do have spherical aberration, but guys, I think some of you, and you're not the only person who kept getting virtual images. I had a lot of people telling me that they were getting virtual images. And look, it just means that the object is too close to the lens. I mean, there's nothing special about my setup here. I'll get a virtual image right now. Oops, well, I didn't want to do that. Okay, well, I will go and where is lens data? There, okay. So I will dock all windows. Okay, yeah, I can get a virtual image. If I were to do a quick focus right now, I could totally get a virtual image, but it's just because my object is too close to the lens. That's all it is.
Okay. Then with this setup, I got better results for my spot size radius when the lenses were flipped from what you currently have.
When the lenses were what?
flipped from what you currently have.
Yeah, this is a pretty terrible setup right here.
Okay.
I was just doing this off the top of my head. But yeah, this is a terrible setup because the larger angles are coming in on the more curved side when the curved side is bending away from the rays. If I were to flip it around, then let's do a quick focus. Yeah, it's a lot further back. It's no longer 4:1, but there you go.
Right.
Any questions? Let's show you a trick. You're not required to use this, but here is a very simple way to get 4 to, oops, that should be 20. Here's a very simple way to force the ratio of those two distances to be 4:1. I would make that a pickup. Pickup just means that you're telling Zemax, pickup means that it's picking up where another surface left off. It's basing it off of information from a previous surface. So I'm going to make the thickness of surface 4 proportional to the thickness of surface 0 by a factor of 4. And if I do that, well, nothing looks in focus here. Well, that's fine. It's not in focus yet, but I could do two things. One is I could systematically play with S1 and figure out what S1 would need to be so that it's in focus while this 4:1 ratio is ensured. Or I could just tell Zemax to do a quick adjust. And when it does that quick adjust, it'll change surface 0. It'll change surface 4 accordingly because it has to. And it'll see what happens to the spot size. And boom, that's a really easy way to get my 4:1 magnification. Any questions? This is all perfectly clear. There's one assignment in a few weeks where the pickup will be useful, but in general, there might be two. I don't require you to use the pickup. It's just a very convenient feature. All right, I want to say a little bit about another aberration, field curvature. It's most pronounced with rays that are pretty far off axis. So in the situations I'm usually interested in, microscopy, that's what a lot of my research is focused on. Spherical aberration and coma are more important, followed by astigmatism, followed by field curvature. But in photography, field curvature is pretty important because photography, the angles are going to be pretty wide. I mean, there's always fine extreme close-up. I'm not necessarily talking about super wide angle lenses, but usually the angles are larger than they are in photography, in microscopy. And like I said before, the basic idea is that you've got a flat object and the focal plane becomes curved. And it's called the Petzval surface because it was worked out by some scientist named Petzval. And I'm not going to attempt to prove this, but a fascinating fact is that the radius of the Petzval surface, the radius of curvature of the Petzval surface, is given by this equation. 1/r is the sum of 1/n times the focal length. So for each lens, you take its refractive index, that's the index of the glass, not the index of the air on either side. You multiply it by the focal length, and you sum all of those, and you have the Petzval curvature. And it's actually a little bit tricky to verify this equation because spherical aberration and coma can also complicate this. All of this is assuming a lens that's been reasonably well corrected for spherical aberration and coma, or angles so large that spherical aberration and coma are not dominant compared to field curvature. But this is why many optical systems will have negative lenses in them. There's a famous lens called the Cook Triplet. It's a trio of lenses that was invented in the 19th century. And for many years, it's been the basis for a lot of different photography lenses. And the Cook Triplet has a negative lens, a concave lens in the middle, because, well, its focal length is negative. So you take, if we do that Petzval sum here, we take 1 over 2 positive numbers, plus 1 over a negative number, 1 over a positive, plus 1 over a negative, plus 1 over a positive. And depending on the values of those positive and negative numbers, you could potentially get 0 field curvature. Any questions? Let's see if there's anything else in these slides that I want to show you. So here's an example. Again, these are borrowed slides from someone who put them on the internet for use, Richard Jurgens. Original object. This is actually a pretty common object. It's called the US Air Force test pattern. It was designed by the Air Force as a common benchmarking for imaging systems. People use versions of this in everything from microscopy to satellite imaging and everything in between. They use different scaled versions of this. It's not just used in defense contractors. It's one of those things that gets used throughout science. Here's the effect of spherical aberration. Just kind of blurs everything out uniformly. Here's the effect of coma. Coma gets worse the farther off axis you are, whereas spherical aberration is the same everywhere, because spherical aberration only depends on the aperture, whereas coma depends on the off-axis distance. So in the center, coma isn't too bad. It's barely noticeable. Out here, I don't know if we could look at it and say, oh, that's clearly a teardrop shape. But we could definitely look at it and say, yeah, the stuff out here is blurrier than the stuff in the middle. Astigmatism produces elliptical shapes, and we can definitely see something kind of asymmetric as we get out to the edge. Distortion is a kind of warping. And field curvature, again, is a blur that gets worse going out from the center. And in reality, you never have just one of these, but there are recipes for correcting each of them. Any questions so far?
For astigmatism, it was kind of hurting my eyes. Is it because my eye is trying to fix the astigmatism itself? And how is it trying to do that? If it is?
Okay, I didn't notice that before. I don't know if it's psychosomatic or I'm just noticing for the first time, but yeah, I'm having the same thing too. I can sort of feel a little bit of pain in my eyes. That is an excellent question.
I'd wonder, like, how is my eye trying to fix it?
Well, your eyes are trying to focus in some way, and so all of those different muscles are working. And eye strain is nothing to take lightly. It's actually a cause of headaches for some people. Eye strain headache should not be confused with what's it called, ocular or ophthalmic migraines. That's a different thing altogether, where the light signal in the retina triggers something neurological that people way above my pay grade can explain. But eye strain comes from the muscles, and that can definitely be a source of headaches. Yeah, ooh, that is kind of, okay, I'm sorry, everyone, I'll turn it off. Other questions that don't involve a visit to the neurologist? I see someone tried to say something in the chat. Where is the chat box not showing up? I can't find my chat box. Oh, well, I'll look at the comment later. Okay. Field curvature. I want to say a little more about field curvature because it's one of the easier things to correct just by having 3 or even 2 lenses. And let me share my other screen. So 1 over the radius of the curved focal plane is the sum over all the lenses of 1 over ni fi, for lens I is the number of the lens. Well, here's a very simple combo of lenses. Minus f plus f separated by a distance d. And assume, for simplicity, that they're made out of the same type of glass. If they're made out of different types of glass, then we might have to also adjust their focal lengths to be slightly different, but that's an aside. Okay, we derived a few weeks ago in class a formula for the effective focal length of a system like this. And the basic idea was that we could figure out, we send in rays of light and they are going to diverge. Parallel rays of light are going to behave as though they were traveling from some point back there. And then we could, and I know I'm not doing any of the ray tracing here correctly, but we could figure out how far off axis this image forms, and that will be equal to the effective focal length times tan theta. And when we did that, we found that 1 over f effective is equal to 1 over f1 plus 1 over f2 minus d over f1 f2. Well, in this case, that's going to be 1 over minus f plus 1 over f minus d over minus f squared. These two cancel out. And the minus sign up top cancels the minus sign down there. And we're left with d over f squared. So it turns out that it is indeed possible with just 2 simple lenses to design something that has no field curvature. What that means is that wherever this focal plane might be, assuming that the rays are not too far off axis, so we don't have to worry about spherical aberration or coma, if we sent in a bunch of rays at different angles, they would come to a focus in a plane rather than a curved surface. Any questions? This is one of the main, not the only, but one of the main reasons why you will see so many concave lenses in real lens setups. Now I want to turn to the upcoming Zemax assignment. So let's look at that. Project 5, correcting spherical aberration. Okay. I said last week that there is a rule that is quite tedious to derive, but it's rather simple to state, that you can minimize spherical aberration, meaning that you minimize that coefficient of r cubed if the lens parameters obey this relationship. And you already saw something along those lines. You didn't necessarily achieve something that was rigorously a minimum, but you did at least find that there are some scenarios where the coefficient of r cubed is smaller than in other scenarios. Well, now what we're going to do is we're going to play with some lenses by trial and error, and we're going to keep playing with them until we have optimized them for a particular S2 and S1 value. And we're going to see, okay, we play around with R2 and R1 until we minimize the spot size for one pair of S2 and S1 values. Then we're going to try a different pair of S2 and S1 values. And we're going to, again, optimize R2 and R1. And we're going to see what happens. We're going to keep on doing that. And for each S2 and S1 pair, we're going to make a graph that has this thing on one axis and this thing on the other axis. And we're just going to see, is the slope equal to this thing here? Any questions on that idea besides the obvious question of, well, how are we going to try all these combinations? But other than that one, which we'll get to in just 1 minute, are there any other questions on the idea of the assignment? Let's go into the thing called the merit function test. Zemax makes it easy is a strong term. Zemax has a way of testing all those things for us. If computers are good at anything, it's crunching a whole bunch of numbers a whole bunch of times in a row and seeing what happens in each case. So here's a lens. And I have designed this lens so that it is plano-convex. And it's biconvex. I was staring at the P. It's biconvex, and not just biconvex, but actually symmetric. So the radius of surface 2 is -1 times the radius of surface 1. Okay, well, that might not be the optimal shape. So what we're going to do instead is we're going to tell Zemax to make this a variable. We're going to also make this one a variable. Does anybody need time to open this file?
Oh, I do.
All right, I'll give you a minute to open this file. No, that doesn't help. Really, I think this whole place is just destined to always kind of, no, well, whatever. I don't know, I'm not aesthetic and into lighting and stuff. Maybe I should string white Christmas lights on my ceiling. Maybe that would make them more uniform. I'm up in my loft is the thing. Anybody still need time? Going once, going twice. Okay, so we've got something set up for a particular S1 and S2 combo. And like I said, we just want to see what pair of radii will give us the smallest spot size. So first of all, we have to tell Zemax that these radii of curvature are variables for it to play with. It's not going to play around with anything unless we tell it to. It is a very well-behaved, respectful program that only touches the things that we designate as adjustable variables. It leaves everything else alone. Then we have to create something called a merit function. So we're going to go to the optimization wizard. That's under optimize. And there are a few different ways to optimize an image quality. We are only ever going to deal with wavefront and spot size. Spot size is something we already know. It's just what's visible right here. Wavefront error, well, let's think about it this way. We haven't dealt really with the wave nature of light yet, but we know that by the principle of least time, all of the paths, ideally, all of the paths from object point to image point should take the same amount of time. And we know that when there are aberrations, all of those paths don't take the same amount of time. And so wavefront error is basically a way of quantifying what that error is. It's a way of quantifying just how much do the paths differ in time. And they express those differences in time in terms of the frequency, or in terms of the period of the wave, which is equivalent, being off by one period of oscillation is equivalent to being behind by a distance of one wavelength, because one wavelength is how far it goes in one period of oscillation. Let's just deal with spot size, right? And let's leave everything else alone, because I'll be honest with you, I don't mess around with merit functions that much. You could go into great depth with merit functions, and people who do very elaborate engineering designs get deep into that. I don't. I just want to optimize simple components to illustrate physical principles because I'm a physicist. I like the principles, whereas engineers want to optimize large instruments. And so I'm just going to teach you what is a merit function, what's the idea of it, and then if you go into an optical engineering career, you'll learn more. But the basic idea is you're just telling it, optimize the spot size. Pick something that optimizes the spot size. Any questions?
So we're not adjusting anything else besides the fact that we're choosing spot for image quality?
Yep, we can do
Okay.
spot, or we can do wavefront. We could have it do RMS spot size or geometric, but we're going to do RMS. We could have it measure that spot size relative to the centroid, or something called the chief ray. We're just going to go with the center of the spot. And it's warning us that some field positions have 0 weight. Well, that's fine. All right, let's hit the optimize button. It wants permission to start. We give it permission to start. It played with 2 variables. It tried to reduce this merit function from 0.0095 to 0.00868. And it did that in 1/8 of a second. We exit, and we see that the lens shape did indeed change. Right? Whereas before it was symmetric, now it is asymmetric. And sure enough, when we look on here, we see that one side is less curved than the other. Do you get similar? Is anybody not getting these results when they try to run the merit function? remember what I was saying earlier about how if it's going to hit a side, it's going to hit a more curved side. There's going to be one side, there's almost always one side that's more curved than the other. It's going to try to set things up so that it hits that side when it's making a smaller angle. That's what we got in this case. On the more curved side, the image is farther away, and so all of the rays are making a smaller angle. That might not be as noticeable. So let's do a quick focus for a smaller S1. All right. We've got a more extreme ratio. I'm going to move this in even a little bit further. I want to do, no, I'll go back to 8. Quick focus there. Yeah. Okay. And let's move field to, well, you'll see why. Let's do optimize again. And sure enough, when we optimize again, we see that the shape changes again. And it remains the case that the larger angles, the rays making larger angles, hit a flatter surface, and the rays making smaller angles hit a more curved surface to try to keep everything balanced. That's a rule of thumb. That's a design rule of thumb worth keeping in your head. The question of what exactly this radius should be, you let a computer do that nowadays, but you have to think about, well, which side do I want it in general be more curved and design around that? And then you hone the specific numbers via trial and error. Somebody must have a question.
I think I'm just trying to follow along with what you just did. So for field 2, we set it off axis by,
Well, let's let me show you something. Let's not play around with field 2 yet. Let's go to analyze, and we're going to do RMS versus field. And what that's going to plot is the RMS spot size. Okay. This was optimized to be fairly flat across the field. Our fields range from 0, meaning on axis in field 1, to 0.5 centimeter off axis in field 2. So that's the range of fields that it's trying to optimize for. It's saying, okay, I've got a field that's completely on axis, a field that is 0.5 off axis. It tries to optimize for all of those. And the result was fairly flat.
okay.
Yeah.
Wait, so that's all we did? Cause my values and spot diagram look a little different from yours. So I was wondering if you adjusted anything.
Okay, so let's see. You have fields at y equals 0 and y equals 0.5.
Yeah, I haven't actually touched any of the fields. I was up to date with you when you did the first optimization. And then I don't know if you changed anything after that.
I changed the layer thicknesses. Did you change the layer thicknesses?
Oh, okay, yeah, then that's what I was missing. Thank you.
Remember, the
only
layer
change the object
thicknesses
0?
really should affect what's going on, because optimizing for different magnifications will require different kinds of optimization. Justin, you had a question?
Did you only change object 0? Or, sorry,
No, I
layer
also
0.
changed layer, I also changed the thickness of layer 2 to 34.927.
Gotcha. Thank you. I wasn't sure if that was calculated or not.
That
Oh.
was achieved from the autofocus, right?
Yeah, so I changed this to 8 and then I did an autofocus, but you could just
Ah.
type in 34.927.
But sig figs.
Yeah, fine. You know, you're gonna get ever so slightly different from me, but whatever. Other questions? There should be more questions. This is all just completely transparent. This is as clear as BK7 glass.
I got a question about the RMS versus field diagram. I just have
Okay.
a different y-axis than you. Mine just ranges from 0 to 5.
Because were you doing spot radius or wavefront?
I was doing wavefront. That's why.
If you do wavefront, you get 0 to 5. If you do spot radius, you get 0 to 500.
There we go. Thank you.
No, let's have it optimized wavefront. So let's go back to optimization wizard. Let's have it optimize wavefront and see how different things look. Then we do our, you can ignore the merit function editor. We're not going to go in and touch that. I optimize, start. It changed ever so slightly. And the RMS spot radius versus field, we now see that that's not as flat as it was. But remember, that's not the thing that we optimized for. What we optimized for was wavefront error. And while that's not terribly flat, but it did go down, whereas before it was up at 4, now it's down around 2.5 to 2. So when you optimize for different things, you get different results. That should not be terribly surprising. If you say, I really want to improve this, well, then this other thing might not improve, but you never specify to improve that other thing. When you tell a computer to optimize something, it does that and nothing else. And that is one of the dangers of optimization. And this shows up in human organizations when you say to someone, I want you to solve this problem. And they solve that problem. You know, I do class scheduling and someone says to me, I don't want any empty seats in the class. We need to be efficient, no empty seats. That's the easiest thing in the world for me to do. You don't want any empty seats? I just won't offer enough classes, right? If there's fewer classes than there are students, there are no empty seats. Somebody says to me, well, I don't want that. I'm like, well, you know, we got students who don't get classes. I didn't want you to do that. I say, well, you yelled at me when there were empty seats. Well, we have students who need classes, open classes. So I open classes and then there are empty seats. And someone yells at me and says, why are there empty seats? And I say, because I got yelled at when there weren't empty seats. Computers are the same way, all right? You tell it optimize spot size. It optimizes spot size. You can say, what about wavefront error? Well, you didn't tell me to optimize wavefront error. Or you optimize for this combination of S1 and S2 values, 8 and 35, basically. Well, then somebody says, I'm going to change it to optimize for 20, and I'm going to guess that's about 10. So do a quick focus, and we optimize for that now. and we get a different lens design. Somebody says, you want me to buy a different lens? I say, yeah, because we optimized for a different thing. You want to optimize for this situation, here's the lens you get. You want to optimize for that situation, you get a different lens. Then somebody says, well, I want a lens that's perfect for both. And you laugh at them because there's nothing that's even perfect for one situation, let alone two. Questions so far? But look how flat that wavefront error is. And then we could go in to the optimization wizard. And we could decide to see how much are things going to change if we optimize for spot size. Now let's just find out. Right now it's 5.53 and negative 9.161. And it barely changes. That's good. Now I want to show you something else. What if we optimize this? I'll give both of these weight 1. It can't handle a weight of 0 in the merit function. It gets confused. All right, so I'm just going to make the range of fields 0. So it's only going to optimize now for a range of 0. First of all, notice that my RMS versus field, you're thinking, oops.
Sorry, what does weight mean?
Weight means how much consideration to give it. The weighting is used in the quick focus and the quick adjust. The merit function editor can't handle 0 weights, so it kind of ignores when you say 0. But let me, you know what, here's how I'll explain the weighting. Let's go back and move this field off axis, okay?
Is it like how it finds like the average position of the image between two focal points rather than like the exact focal image that it would normally be at for just one?
Yeah, basically, if we were to tell it, forget about the merit function editor, which is what you use to optimize radii. Suppose I just want to focus, okay? Or suppose I just want to optimize one variable. And I just want to play with the S2, the last layer thickness here. If I tell it to give these two equal weight, then what I'm basically telling it to do is not to minimize this spot size or this spot size, but to minimize the sum of the two. Right now there's 75.6 and 93.1. Let's tell it to do a quick focus. Well, one of them went up just a little bit, ever so tiny, not much, but it went up because it was no longer solely concerned with the on-axis object. The off-axis spot size went down because the goal was not just to minimize the 73, the size of this spot. The goal was to minimize the sum of these two spot sizes. Now, what if I decided to give the off-axis object more weight? Right? Do another quick focus. Well, this one goes down by a lot because it no longer cares about this one, but it cares a lot about this one.
We assign a weight of 0, like just say we wanted to keep it there visually, but ignore it for all terms of focusing and whatnot.
To make the weight 0?
Yeah.
Absolutely. You just type the number 0 in there. It's going to cause a few problems with the merit. It's going to get some warning messages from the merit function, but for the quick focus, you'll be fine.
Cool.
And then we give the off-axis object all of the weight, and here's what it comes up with. Whereas if we gave the on-axis object equal weight and we told it to do it again, see what it's basically doing is right now it's optimizing 5 times this size plus 5 times that size, which is the same as optimizing 1 times this size plus 1 times that size. Or I could have it do 5 times this and 2 times that. It's all about, in a trade-off, how much do I care about each one? All right, it's basically telling you, the weight is telling you how much you care about this one relative to the other one. Other questions? Well, I'm just going to make these 1 and 1 again. And I'm going to move this object back on axis. All right. And now I'm going to go into my merit function editor. Sorry, not my merit function editor, my optimization wizard. And I'm basically telling it to apply the current settings. Whenever you update things, you have to go back into the optimization wizard and tell it to apply the current settings. And I'm going to tell it to optimize yet again. Okay. Now I go, so far it doesn't look like anything interesting has happened, but just watch. I told it to optimize for a range of 0. Now I can't actually handle a range of 0, so it handles a range of 10 to the minus 7, which is close enough to 0 that we don't care. But then I'm going to move this object off axis. And what you see is that it actually gets pretty bad for an off-axis object. Why is it pretty bad for the off-axis object after I optimized? Any guesses as to why it's so bad for the off-axis object?
We're optimizing for spot radius, right?
And we were optimizing not just for spot radius, but we were optimizing for an on-axis object. I never told it to optimize for off-axis. My range of fields was 0. Well, it couldn't handle 0, so it made it 10 to the minus 7, which is close enough to 0. 0 sometimes causes it problems in these optimization routines. So it optimized for as close to 0 as it possibly could. It never optimized for off-axis. So off-axis looks terrible. Let's try optimizing for off-axis. Now we've got some off-axis objects. We go in there, we apply the latest settings. We tell, when we do that, we're basically telling Zemax, hey, look at everything that's in there right now and use it. Now, let's optimize. And hey, now the off-axis stuff is as good as the on-axis stuff because we told it to optimize for the average of all of these. right? It didn't optimize solely for on axis or solely for 2 centimeters off axis or solely for 1 centimeter off axis. It optimized the average of all of these. And when we tell it to optimize the average, we get a pretty good result. When we tell it to optimize for 1 point, we get a pretty good result for that 1 point. Make sense?
Yeah.
Somebody must have a question. All right, while you're in this, I'm just going to give you some time to play around with it, optimize lenses for different situations, and see if it makes sense. All right, because between now and next Tuesday, you have to optimize a bunch of lenses and look at their shape factors is what to look at their, oops, wrong assignment. You have to look at their shape factors, which is what this thing is called, and look at this other parameter here and see if a graph has the properties that you expect. I'm going to give you about 10 minutes to play with that, go through the assignment, and I'll take questions as they come up.
Can you set the aperture as a variable, or is that just kind of useless? Just a smaller aperture is better.
That is an excellent question. I don't know. My intuition is saying no, because it's one of those things where we already know the effect. There's no place to set the V there, but to put a V next to it. On the other hand, when we go into the
Wouldn't the optimal setup that would like minimize spherical aberration be just an axial ray? So the wouldn't the optimal aperture just be infinitesimally small?
yeah, except that once you get into diffraction, it gets a little more complicated. So
Could you try putting a surface like before the lens and after the object and tell it to optimize and not let rays go to only go through that surface, and then tell it to optimize the height of that surface based on the spot size? So you'd be controlling like that kind of aperture.
let's find out. Let's go into the lens data. Can I make the clear semi-diameter a variable? They make the mechanical semi-diameter variable. There's no simple way to do it, but I know that the merit function editor is something I've never learned how to use. I know that there's like an entire programming language for optimizing these things and writing scripts and stuff. I assume that there is some way to do that, but I don't know for sure.
Okay, thank you.
What I want to do right now is play with these. So you guys are optimizing one lens. I want to optimize two lenses. Spot size, RMS, centroid, apply. Okay, we will go into the fields and give field 1 a weight of 1. And then we will apply this again. We'll close it. And then we will optimize 4 variables. And it took a little bit longer. And we got, oh, very different layout. Because it's got more variables to play with, it made this one concave on one side, but more convex on the other side, so that the rays would hit the surface not quite head on, but close to head on, and partially change direction. Then they change direction a little bit more here, and a little bit more here, not by much, and then a little bit more there. Oh, that's diffraction limited performance. Because the spot size, the RMS spot size is smaller than the area radius. Very nice. These are not plano convex lenses, so I should save this as something other than convex lens. Anyway, I'm just playing around, but that should not stop you from asking questions. Apply the current settings, close. Let's try optimizing again. Okay, definitely not diffraction limited, but still impressive.
How many magnification values should we test for between the 1/9 to 5 times range?
12-ish, 10 or 12.
Okay.
All right, I'm gonna add a third lens because I feel like there's an Onion article about a razor company executive who said, screw it, we're doing 8 blades. And I'm just gonna make this like 50 and minus 50 to give it a starting point. And I'm going to make this thickness 1, and make this one 60, and I'm going to make this one 1, and make this one pick up from surface 0 by a factor of 4. And we're going to see in the layout, okay, well, clearly I need to pay any attention to those. My layout, And I didn't make this of SF11. And yeah, my layout is really no good, but you know, I didn't optimize any of this. And I make this variable, and I make this one variable, and then I go into my optimization wizard and tell it to apply the current settings. And then I tell it to optimize 6 surfaces, and we exit. We look at our layout, and then we go to our spot diagram, and we're at least approaching the diffraction limit. We're at about a little bit less than 4 times the diffraction limit. It's not terrible. I've seen worse.
Can I ask a quick question?
Sure.
Why is it whenever you set thickness to a variable that it seems to get really big when you optimize it?
There's a reason for that. Okay, the reason is that lens thickness does not have a huge effect on image quality. This is one of the ways that computers are kind of dumb. Because it doesn't have a huge effect on image quality, it has to make huge changes in the lens thickness before it even notices something, before it even notices an effect. And there is a way somewhere in the merit function editor to specify bounds on it. I even knew it at one point. It's in a notebook that is unfortunately in my office. But the reality is that I would probably not want to make glass thickness a variable, partly for that reason, because I know that making it a computer controlled variable is just going to cause the algorithm to run away. And partly because even if I had a smarter computer, even if we had a smarter algorithm, or I remembered what that one setting is, there's just so little gained from it that I would rather pick my glass thickness based on more practical considerations, like how much space do I have in this setup? How much weight tolerance do we have? Glass is heavy. You know, given that this variable won't make a huge effect on the optics, I would rather pick this variable based on other considerations.
Okay, so seems more of like a engineering mechanical standpoint to change the thickness of the lens.
Basically, because it has, in most cases, I mean, when I use the word most because someone can always find an exception, but in most cases, it doesn't have a huge effect. Well, it doesn't have a huge effect on the focal length of the lens, unless you're in an extreme situation. It usually doesn't have a big effect on the aberrations. I mean, it has some, but it's a pretty small factor in a lot of things. And all of these optimization algorithms, what an optimization algorithm is trying to do is find the minimum of a curve. I mean, if we were to imagine that the spot size or whatever measure of image quality you're using is a function of several variables. Well, we're trying to either minimize something or maximize something. And so we're trying to find a point where the derivative of something is 0. So we're moving along a curve. Here, I'll do some annotation on my screen so that I can draw. Okay, so we're drawing a function of many variables. I'm just plotting one of them. And if I need to figure out how far to go here, I'm going to extrapolate if I'm trying to find that peak, I'm going to take a step forward from here to here and see, okay, did I improve? Then we take another step. Did I improve? Then we take another step. Did I improve? Then we take another step. Did I improve? Oh no, it got worse. I should backtrack. And all of these steps depend on values and derivatives. Depends on the value of a function and the derivative of a function. And if some of the derivatives are 0, then at some point in these calculations, you wind up with division by 0 and things blow up. And so dividing by a small derivative means that a step size could blow up. And that's common in a lot of optimization problems. And all these things that I'm saying about optimization problems, they also show up in machine learning. You know, you tell something to look for patterns, and it will look for patterns, and it might find that the only way to change something is to make a really big change. Likewise, it can be lazy. You know how I said that, well, sometimes the easiest way to solve a problem is to just run a huge number of classes or run like no classes. You know, if you only give me one thing I have to optimize for, I'm going to do that because I don't want to get in trouble. One machine learning algorithm, there's a famous case where they wanted to train a machine learning algorithm to analyze X-rays and see if they could spot a particular kind of disease. Well, apparently all the patients with that disease or that injury went to a particular hospital. And the X-rays had a little stamp on them saying, such and such hospital name. Well, the machine said, okay, the only people who ever have this disease, or almost all of the people who have this disease, are at this hospital. So it just started looking for that stamp and said, if it's got that stamp, I'll diagnose them.
The hospital stamp?
Yeah, if it's at such and such community hospital, you know, Northwood Community Hospital has all the people with this disease, whereas Southwood Community Hospital never gets the people with that disease. So the algorithm just said, okay, I guess the name of the hospital tells you if you got the disease or not.
Correlation doesn't mean causation.
Yeah, so optimization algorithms are quite dumb.
Okay, that makes sense. Thank you. And also, I think I found where you could set that boundary condition in the merit function. It's just right when you open the optimization wizard, it just says boundary values right on the side. You just check mark glass and then enter them.
Okay, boundary values, and those are for
Yeah, so I just
edge
checked.
thickness, or but are those minimum and maximum radii, minimum and maximum thicknesses? What
Well,
are they?
for the glass, I just did it with my glass sample. So I checked glass. I set my maximum to 10, and it was originally at 20. Then I ran the optimization function, and it changed it to 10. So.
Oh, it changed the thickness. So that, okay, so you're saying you did it. Which one did you change, max or edge thickness?
Max.
Okay, good to know. Let me see. I don't think I have. Yeah, I don't have any thicknesses as that. Any other questions on the optimization wizard at this point? Then let's take a break until 6:25, and then I'm going to show you a very special perfect lens. We'll see you in about 7 minutes. That was not what I expected. Not what I expected at all. I did not expect that at all. Okay, so I wanted to talk about one other aberration, and I should have talked about it sooner, and that is chromatic aberration. I now am learning the hard way that it's not quite doing everything that I thought it would do. So we go into our optimization wizard, and I've just told it that we've got a third color. I'm having it apply the current settings. And then I tell it to optimize for that third color. And when I do that, wow, things do not look, let's have it show all the wavelengths, and let's have it color them by wavelength. And yeah, what your lesson should be is that chromatic aberration is a real terrible thing. And I will explain what that means in a moment. But chromatic aberration is indeed pretty terrible. So the basic idea is that different glass can have different refractive indices for different wavelengths. And as a result, if you try to optimize for one wavelength where it has one refractive index, it could be absolutely terrible for all of the other ones. And so you end up with these absolutely hideous spot diagrams where we are more than 100 times the diffraction limit in size. And nobody would even consider this to be acceptable imaging. And so what people do in situations like that is they try to combine a few different types of glass, right? And I think that rather than trying to invent it on the fly, we should just take advantage of one of the nice built-in features of Zemax, which is that we should go to the documents that they make available to us. So on Windows machine, we're going to open a file. It's going to be under probably your documents folder, and at least in Windows 10. Zemax samples sequential. That just means one object after another. We're not going to play with beam splitters or things like that. And we will do miscellaneous. Objectives. Let's do doublet. And when it loads that doublet file, there is a whole bunch of analysis to be done. A doublet is exactly what it sounds like. It is two lenses together, sometimes literally cemented or glued together, made out of two different types of glass. And the idea is that although they both have different refractive indices for different colors, and this means that the focal length of one lens is going to change as we change the wavelength, the focal length of the other lens also changes when we change wavelength. And crudely speaking, these changes cancel out. To see why, let's go to dispersion diagram. And it is always going to start with the first thing in alphabetical order in the catalog. So we'll just switch it to BK7 for glass 1 and F2 for glass 2. And I don't claim it is at all obvious that the combination of these glasses would work, but it does. The basic idea to think about is that one of the focal lengths will increase or decrease by a lot, and the other one will change by just a little bit. And one of them will drop a lot, and the other one will just drop a little in such a way that it balances out. And if we look at the focal length shift, they often draw their diagram. Optical engineers often draw diagrams like this. They draw on the horizontal axis how much the focal point shifts, and on the vertical axis, they draw the wavelength. And you might think, well, that's a pretty big curve. Yeah, it's a pretty big curve, except that the focal shift is in microns, or thousandths of a millimeter, or millionths of a meter. So not that bad. Another example, any questions on that example? Then let's open another example file. Not going to change that. Let's look at the just check something. The Cook Triplet. It says Cook 40-degree field. The Cook Triplet is a highly optimized lens. It's a famous design from the 19th century that I alluded to. And it's a combination of 3 lenses. They again made it out of just 2 kinds of glass. Some people will now make them out of 3 kinds of glass, but a combination of 2 works pretty well. And let's try to see how this works. So we go to our libraries. They chose a different glass. Instead of BK7, they chose SK16. So let's pull up a dispersion diagram. So the first one will be F2. And the second will be SK16. And here you can see that one of them actually has a higher index, that they actually swap which one is the high index and which one is the low index. And that helps with the compensation. Let's go to analyze. And now I am trying to remember where the focal length shift is. Chromatic focal shift. And again, you can see that this has a focal shift on the order of a few tens of microns, the same as the achromatic doublet that I just showed you. Any questions? Anyone? Going once, going twice. Let's test something. I said earlier in class that these lenses are designed in order to have zero field curvature. And the formula for zero field curvature was that the sum of 1/n times the focal length has to equal 0. Let's see here. With our first lens, it's not quite plano-convex, but it's darn close to plano-convex. So we've got SK16 glass. SK16 is the green one. We'll just work at 550 nanometers. So about there, SK16 is the green one. So we've got 1.622 minus 1 over F. Here, I'm going to type all this and annotate. Equals 1.622 minus 1 divided by 1.622 times, quit out of annotate. You know what? Doing it in annotate is a terrible idea. And NSK 16 equals 1.622. Actually, both of them are about 1.622 for our purposes. So N equals 1.622. R1 is 22.014. R2 is minus 435.760. R3 is negative 22.213. R4 is 20.292. What I'm doing right now is I'm entering all the information that we need to calculate the focal lengths. Okay, so F1 equals 1 over um, 0.1 over n minus 1 divided by R1 minus n minus 1 divided by R2. Of course, I didn't know that. F2 is 1 over n minus 1 over R3 minus n minus 1 over R4. And F3 is equal to 1 over n minus 1 over R5 minus n minus 1 divided by R6. And now let's just do 1 over F1 plus 1 over F2 plus 1 over F3. And that is very close to 0. And you could say, well, it's not exactly 0. You're right, it's not exactly 0. But keep in mind that I didn't keep all of the decimal places. If I were to do this more accurately, it would be 1.62298. Let's change that. We'll do that. We'll do NSK16 is 1.62. 261 actually. And NF2 is about 1.62398. Barely changes that. And let's see if this improves things. Not really, but it's still pretty small. And remember, this is a trade-off over several wavelengths. So we shouldn't expect everything to be perfect at any given wavelength. Okay, so what do I want you to take away? What I want you to take away is that people will design lenses in such a way, or design combinations of lenses, so that one lens has a focal length that changes. One lens is made out of a material whose refractive index changes very drastically. The other lens is made out of a material whose refractive index changes more slowly. And you might be thinking, well, if all of these changes are negative, mean that it's always declining as you go out to longer wavelengths, what's the point? Well, the negative lens over here, when we change the focal length, we are changing a negative number, right? We're multiplying by negative numbers because of the radii of curvature. So even though the change in n always has the same sign going from blue to red, n is going down. It's n over r that matters. Any questions? All right, I want to show you one last thing in the last few minutes. There's a third Zemax file. And that is for something called an aplanatic lens. Let me get rid of this annotation. Okay, what we've got here is this clear semi-diameter and the mechanical semi-diameter should have been 8 and 17, and let's see if that fixed it. I'll worry about the rest of that later. Let's just show one field. Okay, if we just show one field, for that one field, we actually have perfect imaging. We can verify that. We can zoom in. No matter how much we zoom in, we have to zoom in a whole lot before we get anything other than all of the rays coming together. If we look at a spot diagram, we see that the area radius, which for now you just need to know is the fundamental limit to how small we can focus light, that the area radius is a minuscule fraction. Sorry, that the spot size is a minuscule fraction of the area radius. And this is one of the few cases where you can do perfect imaging without a Cartesian oval. All right, this is one of the few cases where you can do perfect imaging just with spherical surfaces. There is a special point in a sphere called the Applinetic Point. And if I had more time, I could do the derivation, but it's a not terribly enlightening exercise in geometry. You can look it up. All you need to know is that it's slightly off center in the sphere. But it's slightly off center in this outer spherical surface. The inner spherical surface, if you look carefully, these rays are hitting it head on. So there's no refraction here, all right? They're hitting it at normal incidence. When a ray hits a surface at normal incidence, there is no refraction. To see what I mean here, I'm going to make this SF11. I'll make this SF11. And what I've got for now is I've got rays that are embedded in glass. I've got an object that's embedded in glass. And the rays are just passing through an interface that we won't even think about for now. And once they because it doesn't matter, it's just an interface between two layers of the same glass. Once they hit air, they spread out. And they act like they're coming from here. But that is a perfect virtual image. Can anybody think of what you might do with a perfect virtual image? I mean, it's not a place where you can put things, right? You can't put anything there. Anybody think of an application for a perfect virtual image?
3D glasses?
What?
3D glasses?
Yeah, that's one possibility. Can anybody think of an application for it though with real imaging, meaning the formation of a real image, a focused image, something related to aberrations, which we've been talking about? Any ideas? I don't know why this extra thing is here. This extra thing bugs me. Ah. Bugs me so much. Okay. Well, let's see here. You tell me, what's making a larger angle? This ray coming from the object or these image rays? What's making the larger angle?
The object's rays.
Yeah. See what we've done? We've just flattened the rays. We've just reduced the angles. So I could put another lens out here on the right and then focus the rays on the right, and I should get fewer aberrations than I would have gotten if I had just collected this angle of rays. So if I collect rays over this angle with an ordinary convex lens, wide angles, terrible spherical aberration, right? But if I flatten those rays, I reduce the spherical aberration. I can't get rid of it, but I can reduce it. And that is the point of these aplanatic lenses. And there are actually people who make things called aplanatic objectives, where that's a microscope objective, and one of the first things they do is the rays hit a surface like this, they get flattened, and then they have a bunch more aberration corrected lenses to at least partially compensate for that. So get as good focus, they get a bunch of aberration corrected lenses to focus what they have, but those aberration corrected lenses have an easier task because the rays are coming from here, making a smaller angle. Any questions? Okay, we're out of time. On Thursday, we're going to start talking about matrix optics. So if you haven't already done so, please install Mathematica on your machine and have a good day.
Thank you.
You're welcome. Corey, you have a question?
Sorry, my computer just froze a little bit here. We're about to leave right now.
Okay.
Thank you.